Hello everybody, and we are back to stoichiometry. This time we're going to be analyzing gas stoichiometry. And if you remember earlier this year, we learned about volume to volume problems, mass to volume, and volume to mass. Now when we learned mass volume and volume mass, we learned how to do those under STP conditions. If you recall, STP, which is standard temperature and pressure, there is a conversion factor called the molar volume, which states that if you have 1 mole of any gas under STP conditions, that it occupies a volume of 22.4 liters. So the conversion factor is that 1 mole is equal to 22.4 liters, as you can see right over here. Now, what we will see this time is what happens when it's not at STP. If it's not at STP, first it will state that. But more importantly, if it's not at STP, they're going to have to give you in the problem the temperature and the pressure that it's going to be under. Okay, they have to give you that information in order for you to complete the calculation. And instead of using the 22.4 liter conversion factor, we're going to use the ideal gas law when it's not at STP. So first, let's review the 3 that we've learned before: volume, mass, volume, and volume, mass at STP. And then we'll transition and we'll do the stoichiometry when it's not at STP. So if you recall, this is a flow chart on how to do a volume to volume problem. It's the exact same amount of steps as doing a mole to mole. It's a 1-step problem. Remember that A is the given, B is the unknown in the way that I taught you how to set this up, and B over A is the key. It's the mole ratio. In this case, it's the volume ratio, but it's the same as the mole ratio, which is the coefficients from a balanced equation. That's why it's important that the chemical reactions are balanced. If they're not, that would be the first thing you need to do, would be to balance the equation. So let me give you a quick example here of a volume to volume. Let's say that we were making ammonia gas. So we had hydrogen reacting with nitrogen to form ammonia. And let's say that this is a 3 here. Let's say we need to balance this, so we would have to put a 3 here, so we can have 6 hydrogens on both sides. If I put a 2 here, actually, I skipped a step there. So if we put a 2 there to balance the nitrogens, and then we have 6 H's on both sides, that would be balanced. So imagine if the problem went like this. I would like to know how many liters, that would be volume, okay, of ammonia, which is NH3. So how many liters of ammonia are produced when, let's say, 12.8 liters of hydrogen reacts with nitrogen gas. Okay, so here it doesn't really matter if it's at STP or not. We can just use the B over A conversion to get the answer. Now let me go ahead and set it up here. When they ask you how many liters of ammonia, that's what we're looking for. That is our B. So we're looking for ammonia. The given in this problem is the hydrogen. It says that we have 12.8 liters. So that's going to be our given. That's our A. So if you follow the flow chart, here's what I'm going to do. I'm going to put the volume of A, which is given, is 12.8 liters, and A happens to be hydrogen, times B over A, which would be the coefficients of a balanced equation. So the coefficient of B is 2. We have 2 moles of ammonia. The coefficient of A is 3. We have 3 moles of hydrogen. And when you do the math, which is pretty simple here, you just go 12.8 multiply by 2, divide that answer by 3. And then we want to round to 3 significant digits since the question has 3. And you end up getting 0.53, and that would be the units would be liters of ammonia, and that would be our answer to this volume to volume problem. Okay? Now, let's move on, and this is the flow chart on how to do a mass to volume. So, again, the first thing you got to do is always convert from grams to moles. So you do that by dividing by the molar mass. That's your first step. Once you get to moles of A, which is the given, then you're going to multiply by the mole ratio, which again is the coefficients, to get the moles of the unknown, which is B. Now, here is where the STP comes in handy. To go from moles to volume at STP, all you got to do, and I'll set this up for you when I do a problem, is you end up multiplying by 22.4. There are 22.4 liters in 1 mole, so when you multiply by 22.4, you will get the volume of the unknown. So let's take a look here at a sample problem. Here we got the making of water, and they want to know how many liters of oxygen. Notice it says STP. So oxygen is what we're looking for. So let's call that B. Okay? And we're looking for liters. As you continue reading the problem, the given is water. We got 10.5 grams of water. That's your given A. So if you follow the flow chart that I gave you, the first thing you're going to do is we're going to convert mass of A into moles of A. Okay? And then we need to find the molar mass of water. Now remember, do not use coefficients to find molar mass. For water, there are 2 hydrogens. Each hydrogen is 1.01. So the total of the hydrogens is 2.02. There is 1 oxygen, which is 16 from the periodic table. When you add this up, your molar mass is 18.02 grams per mole. So let's go ahead and convert the grams of water. If you divide by the molar mass, which is 18.02 grams per mole, that is going to give us the moles of water, which ends up being 0.582686. We'll round later on. This is your moles of water. Now, the next step is to go from A to B. So we're going to multiply by the mole ratio to get moles of B. And the mole ratio here, if you notice, it's the coefficient of B over here is 1, and the coefficient of A is 2. So we're going to multiply by 1 over 2, 1 mole of oxygen over 2 moles of water. And when you basically divide the number I just gave you by 2, you get 0.2913343, and it keeps going, moles of oxygen, which is now B. And then here's our last step. To go from moles to volume, all we got to do is multiply by 22.4. That's the conversion. We're going to find the volume of B. When you set it up, it looks something like this. There's 22.4 liters for every 1 mole. Okay, that'll allow you to cancel units. When you multiply by 22.4, and we're going to round to 3 significant digits, we end up getting 6.53 liters of B, which is oxygen. So 6.53 would be the answer, and that would be a mass to volume problem at STP. Now, let's do the opposite. Let's do volume to mass. When you're doing a volume to mass problem, the first thing you always got to do is convert to moles. This time we're in volume. Because it's at STP, okay, we can use 22.4 liters. This time, however, we're going to divide by 22.4 to get us to moles of the given. Once we want to transition from the given to the unknown, we're going to multiply by the mole ratio, and that'll get us to moles of the unknown, which is B. And then we're going to do the opposite here. To go from moles to mass, we're going to multiply this time by the molar mass of B. Now remember, do not use coefficients when you're calculating the molar mass. So let's take a look at an example. Again, here we have the water equation, and they want to know how many grams of water. This time water is B. They want grams. That means we want the mass of water. The given is right here. We have 1.24 liters of hydrogen. That's our given. That's A. It's at STP. So here's what we're going to do. First, convert the volume of A into moles of A. And the way you do that this time is we're going to divide by 22.4. In fact, let me set it up. You got 22.4 liters of H2. If you set it up, for every 1 mole, there are 22.4 liters. That lets liters cancel. Notice what I'm doing. I'm dividing this time. So you get 0.05536 moles of A, which is hydrogen. We're now ready to go from moles of A by multiplying by the mole ratio to moles of B. Okay? And the mole ratio here, B over A, is 2 to 2. Notice the mole ratio is 2 moles of water over 2 moles of hydrogen. So the number doesn't change. It's still going to be 0.05536, but now it's no longer moles of A, it's now moles of B, which is H2O. Now, if you recall, to go from moles to mass, we multiply by the molar mass of B to get the mass of B. From the previous problem, the molar mass of water, okay, was 18.02 grams per mole. So if we multiply 0.05536, okay, let me see if I can squeeze this in here. Give me one moment as I try to fit this in. Let me go ahead and do it right over here in this little corner. So if we get the moles, which is 0.05536, and we multiply by the molar mass of water, which is 18.02 grams per mole, and we round the answer to 3 significant digits, you're going to get an answer of 0.998 grams of H2O. And that would be the answer to this volume to mass problem at STP. Okay? All right. Now, here's what we're going to do. Here's where it gets interesting. We're going to do a mass to volume problem. And what happens now is it's not going to be at STP. So the only thing that's going to change is this last step. Okay? Instead of going from moles to volume, we're going to use the ideal gas law, which is PV is equal to nRT. That's the only difference. So to go from here to here, okay, we're looking for volume, so we're going to solve for V. If you notice, V is equal to nRT over P. Now, if it's not at STP, they have to give you the temperature. They also have to give you the pressure. These two need to be given to you. Okay? And I'm going to tell you why. That temperature over here will be placed right over here. Okay? Let me do that a little bit better. This is temperature. That temperature will go there and the pressure will go right over there. So, R is a constant. You don't have to worry about R. V is what we're looking for, but N is this number right over here. The minute you get moles of B, you're going to plug it in there. And you're going to have NTP and then, of course, R because it's a constant. And then all you got to do is solve for V. Watch what I'm going to do. I'm going to do a problem where I'm going to go from mass to volume. And instead of multiplying by 22.4 as the last step, everything else is the same. We're going to use the ideal gas law and we're going to solve for volume to get the answer. Okay? All right. So here we have, notice how they give you a pressure and a temperature. They want to know how many liters of oxygen gas form. So how many liters of oxygen, this is what we're looking for down here, okay? We're looking for oxygen, that's B. We want liters. So we want volume. Now the given is we got A over here is 294 grams. All right, so the first thing we got to do is we got to convert grams to moles, okay? Now, if you find the molar mass of KClO3 from the periodic table, K is 39.10, okay, and there's one of them. Cl is 35.45, and then, of course, oxygen, there's three of them, so 3 times 16 is 48, and you're going to get a molar mass of 122.55 grams per mole. So let's do the math real quick. Let's convert 294 grams into moles, 122.55. And when we do that, we get 2.399 moles of KClO3. And then once we get moles of A, then we do B over A to go from A to B. Notice the coefficients are 3 over 2. So 3 moles of oxygen over 2 moles of KClO3, in other words, B over A, gives you moles of B, which is 3.5985, and B is moles of oxygen. Now we already have, this is going to be our value for N, because what we're going to do is, again, we're going to solve for V, okay, and V is equal to nRT over P. Now, the temperature's good. It's already in Kelvin. All right, that's going to go right in here. The problem is we got to convert the pressure, the 755, if you remember. Let's do that quickly. There's in 1 ATM, we got to change it to into ATMs. There's 760 millimeters of mercury. And when you do the math over here, our pressure ends up being let's see here, 0.9934, and that's in ATMs. And that's the number you're going to go put there. And then we already find moles. We got everything we need. Watch what I'm going to do. The moles comes from the problem. Moles of B was 3.5985 moles. That's our N. Our R is a constant, 0.0821 liter atmospheres over mole Kelvin. Our temperature was already in Kelvin at 305. And then at the bottom, our pressure, okay, which we just calculated was 0.9934 moles. So we did that, okay? And when you do the cancellation of units, just like this, okay? And the kelvins will cancel, and notice the moles will cancel. I apologize. Hang on a second. Messed up here. That's ATM. Sorry about that. There we go. That now it's correct. The ATMs cancel. Notice the only thing left is liters. And if we round it to 3 significant digits, you end up getting 90.7 liters as your volume of oxygen gas. Okay, so this was a mass to volume, not at STP. All right, let's take a look at the next question. The next one is, what about volume to mass? What do we do here? Okay, this time, the ideal gas law is used right at the beginning. We don't use 22.4. We got to go, your objective is always to go to moles. Now remember, they're going to give you the pressure. They're going to give you a temperature. This is a must. If it's not at STP, these will be given. Notice what we're looking for this time. PV is equal to nRT. So we're going to solve for moles. Watch this. Moles is equal to PV over RT. So look at why these are given. You're going to plug the pressure right in there. The temperature in here, just make sure it's in ATMs and make sure the temperature's in Kelvin. And the volume that's given goes right here. And R is a constant. You got everything you need to find moles. Once you find moles of A, the rest is identical. You multiply by the mole ratio to get moles of B, and then you eventually multiply by the molar mass to get the grams. Let's go through this step and let's use the ideal gas law at the beginning. Here we have an equation. There's a little typo here. That should be a subscript 2. And it says in this reaction, 4.82 liters of oxygen. Okay, that's our given. That's our A. We got 4.58 liters. Now, they were formed at 745 millimeters of mercury, okay, and 308 Kelvin. So, notice how they give us that they give you the volume of A, they give you the temperature of A, they also give you the pressure of A, which is 745 millimeters of mercury. Okay? Now, we are going to have to convert that eventually to ATMs. We'll do that in a minute. What they're looking for is grams of silver oxide, Ag2O. So that is B. They want grams. This is a volume to mass problem. So what we're going to do is we're going to use, the first thing we're going to do is we're going to use all this information, okay, to find N, which would be PV over RT. All right. Now we got to convert. The Kelvin is fine, but we got to divide this here. 1 ATM over 760 millimeters of mercury. We're going to have to go ahead and do the math here and convert it into ATMs. So when you do that, I get 0.9803 ATMs. So let's plug everything into this equation right over here. So N is equal to P, which we just found, 0.9803, and that would be, let me fix that. That's going to be ATM, just like that. And then V, the volume, is already in liters. Make sure it's in liters. It is. All right. And then R is 0.0821 liter atmospheres over mole Kelvin. And then we got the final thing is the temperature here is at 308. Okay? And when you do the math and you multiply the two numbers on the top, the two numbers on the bottom, you're going to get that your moles, your N, is 0.17755 moles, and this is moles of A, which is oxygen. But we don't want oxygen, we want B. So, how do you go from A to B? Very simple. Multiply by the mole ratio. If you look at the mole ratio, it's 2 over 1, B over A. All right, 2 moles of silver oxide over 1 mole of oxygen, you get 0.3551, and that's moles of B, which is Ag2O. Now, to go from moles to mass, we need to find the molar mass of silver oxide. Well, silver is, there's 2 of them. Each one is 107.9. That gives you 215.8. And there's 1 oxygen, so we're going to add 16 to that. So when you add these two numbers, the molar mass, which I'll write it over here, is going to be 231.8. Now remember, to go from moles to mass, you're going to multiply by the molar mass, which is 231.8 grams per mole. That'll cancel. And our answer, our mass, in 3 significant digits, okay, is going to be 82.3 grams of Ag2O, and that will be our answer for this one. Okay? All right, I will do another review where I'm going to do the 3 class practice problems just to give you a little bit extra. But at least here I was able to show you, how to do mass to volume and volume to mass at STP and when it's not at STP. So you saw that when it's not at STP, you can't use 22.4 liters. The way to get from volume to moles or moles to volume, depending on which way you're going, is by using the ideal gas law. And when you have to do it this way, remember that they have to give you the pressure and the temperature. And when they do, just make sure the temperature is in Kelvin and make sure that the pressure is in ATMs so we can match the units of R. Okay? I'm going to leave you with this final note. I have 3 class practice problems. Here's the first one. I give you the equations already balanced, okay? I want to calculate the mass of aluminum necessary to react completely with 50 liters of HCl at STP. So notice this one's at STP. So I want you to try that problem. So this will be the first one. These are the class practice problems. Here's the second one, and you can pause if you want to do these before you watch me do the solution. This one is magnesium nitride reacting with water to form magnesium hydroxide and ammonia. And notice they're asking you for the volume of ammonia that would be produced at 25 degrees Celsius and 0.950 ATMs. So since they give you the pressure and a temperature, this is not at STP. We're going to have to use the ideal gas law here. And notice the given is if 5 grams of magnesium nitride reacts with excess water. So I want you to try this one again. Again, pause if you want to do this. I will be going over the solutions in another video. Okay, so you could try this one as a class practice problem. And then here's the third one. When heated, you got ammonium nitrate decomposing into water as a gas. This is, just so you know, this is known as steam. Okay, water as a gas and dinitrogen monoxide. So they want to know what mass of ammonium nitrate is required to produce 10 liters of steam at 25 degrees Celsius and 752.4 torrs. Notice again, I gave you a pressure and a temperature. It doesn't even say STP on this problem. So you know we're going to have to use the ideal gas law to this one, to do this one as well, because it's not under STP conditions. So go ahead and try these 3. And in another video, I'm going to give you the solutions to these 3 class practice problems. Okay?